In this video, we're going to walk through an overview of Chapter 6, which touches a lot of different topics. We talk about energy and the units of energy and what that means. Then we talk about that in the context of a chemical reaction and how the energetics of that influence if it releases heat or if it absorbs it. And then we talk about those reactions in more detail and look at reversible reactions and what that means for the concentrations of reactants and products. So let's start with energy. Energy is really potential energy or kinetic energy, where kinetic energy is the energy of motion and moving around, and potential energy is stored energy. We usually think about that as the energy stored in chemical bonds. And it's really the ability to do work is what it is. And we won't go into too much detail with that because that's for a physics class. We're going to focus on just a few aspects of it. One is the changes in energy for that stored chemical energy in bonds, and the difference between reactants and products in a reaction. And so we need some units to talk about that. We have, for talking about energy in chemistry, we typically use the joule. And 4.184 joules equals 1 calorie. And calorie might be something you're a little bit more familiar with, but be careful because 1 calorie is really, let's actually say 1,000 calories. Let's do it like this. 1,000 calories is equal to 1 kilocalorie. Just a metric conversion. But a kilocalorie is what we call a nutritional calorie. And that's the calorie that you read on the back of a package of snacks. And the only way we distinguish it on the packaging of a snack is a capital C rather than a lowercase c in the word calorie. So I'll always write out, for clarity in this class, nutritional calorie. So we want you to be comfortable converting between calories and joules, and also applying them to something that really actually does apply to the health field, which is nutrition. And again, we won't go into too much detail, but we will break down the energy content of protein, fat, and carbohydrates. And you've been provided a table of the amount of energy per gram that you have for these three types of nutritional molecules, and they'll vary amount. And we give that to you in both calories and joules. And so being able to calculate the number of joules in a milkshake is something we expect you to be able to do in this class. Now, energy we're going to use when we compare reactants and products, stored potential energy in their bonds, when we look at a reaction. And so enthalpy is really the amount of energy that it takes to break and form bonds in a chemical reaction. So if we have an enthalpy that has a positive value, we call that type of reaction endothermic. It means that for the reaction to occur, the reactants need to absorb energy to form the products. And that energy is usually heat. If we have a negative value for our enthalpy, which we abbreviate delta H, we have an exothermic reaction, where we release energy as heat to form products. And reactions that are endothermic versus exothermic will behave differently, especially when we think about later reversible endothermic and exothermic reactions. If you're holding an endothermic reaction, like if you're holding a cup where an endothermic reaction is taking place, it will feel cold to you as you're the surroundings. It'll be stealing your heat and warming it itself up, but it'll be taking your heat, so you'll feel like you're getting colder. And for an exothermic reaction, if you're standing near it or you're holding a cup when one is taking place in it, it's going to feel hotter to you. And you're the surroundings, you're not the reaction. Now we can track enthalpy in reaction diagrams where we actually compare the energy of reactants and products. And these are going to have the format, let's move this up and give it a little more space here, where we always have our reactants versus our products. So we'll have reactants and products. And we're looking at a scale of energy. And it will take some amount of energy to break all of those bonds and start forming new ones. And we think of this as a barrier or an activation energy, which is really the difference in energy between the potential energy of the reactants and the amount of energy it takes to have the reactants bonds half broken and the products bonds half formed. We abbreviate it EA. Now, this is a reaction where our reactants and products are at the exact same energy. This is not exothermic or endothermic. So if we typically have one or the other. An exothermic reaction will have a pattern like this, where our products are lower in energy than our reactants. And our enthalpy, so here our enthalpy is equal to 0. Here our enthalpy will have a negative value because those products are at a lower energy. And for an endothermic reaction, our products will be higher in energy. And so we'll have an enthalpy value. And again, that's just the difference between the energy of the reactants and the energy of the products. It doesn't take into account the transition state. That's measured by our activation energy. In our endothermic reaction, that enthalpy value will be positive because our products are at a higher energy level. So that's about what I want you to take away from reaction diagrams, where products and reactants are relative to each other, and then that there's an activation energy that's higher in energy than the reactants or products, and that our enthalpy can be seen as that difference between the reactant and product energies. So let's talk now about reactions, and they can actually be reversible. In fact, most of them are reversible. Ones that are irreversible just mean that it's really unlikely that the reverse reaction would occur. The one that comes to mind is a campfire. When you burn carbon and hydrogen fuel, and it forms carbon dioxide and oxygen and like floats away, I see that as not something that will go in the reverse direction where those molecules will come back. So for a reversible reaction, we're going to use a different arrow. It's going to look like this, where it's a half arrow going one direction and a half arrow going the other direction. We'll still have our reactants on the left and our products on the right. But since this reaction can go both ways, that's kind of relative, right? You could rewrite this reaction flipped. And we expect reactions to go both directions. And if we have more products, then we think of that balance between the two reversible reactions is favoring the product side. And if we have more reactants around, we expect we say that balance favors the reactants. And we track that. We track that with a constant called K. This is our equilibrium constant. So if this equilibrium constant is less than 1, we're going to favor reactants. And if the equilibrium constant is greater than 1, we'll be favoring products, which means there's just more products around than reactants when this comes to equilibrium. And this idea of equilibrium is interesting. When things come to equilibrium, it means that the reverse and the forward reaction are still happening at the same rate as each other. And so that means that as much as you're forming reactants, you're forming products. And so it looks like on a macroscopic level that nothing's changing concentration-wise. But actually, the reaction is constantly happening the whole time. And I liken this to two things, kind of depends on what you prefer, but they're both birds. If you've ever seen a duck swimming in a creek against a current, they can be swimming and swimming and swimming, but they won't actually be moving relative to you on the shore. Same thing with a seagull. If on a really windy day, it'll flap and flap and flap into the wind, and it won't actually make any translational progress. And that's equilibrium. So I'd like you to be able to calculate K if I give you the equilibrium concentrations. And we're going to then use that K to also think about Le Chatelier's principle. So K is the equilibrium constant that characterizes that balance between reactants and products. And it'll be unique for every reaction. The way we calculate K is going to be equal to the concentration of the products over the reactants. And we're going to have exponents here that correspond to the coefficients in our balanced reaction. So then let's focus on Le Chatelier's principle. Le Chatelier's principle states that if our reaction is at equilibrium and it's disturbed, it will go back to equilibrium. So let me write that down. So if I have everything in balance at equilibrium, but I increase the amount of my reactants, I'll form more products until I get that same balance back for a ratio of my concentrations. And these concentrations are going to be described by units of moles per liter of the solution of the reaction. And so with Le Chatelier's principle, we're going to be looking at a couple different changes to concentration of reactants, changes to concentration of products, and changes to concentration or changes in temperature. We're not going to worry about changes in pressure because we really haven't covered gases at all. Haven't we've covered concentration yet. But so thinking about the concentration of a reactant, if either reactant's concentration increases, then you'll form more products. And we call this shifting right, to the right side of the reaction. And if we decrease the amount of our reactants, we will then form more reactants to reach that balance again. And we call this shifting left. And that's the reaction is shifting equilibrium to the left so that way more reactants are formed to remake that balance. So that's what happens when we have our, when we change the concentration of our reactants. And the concentration of our products is very similar. If we increase the concentration of our product, we will form reactants. And that means we're shifting the reaction left. And if we decrease the concentration of one of our products, then we'll form products and shift right. And I don't have to increase the concentration of both of my reactants or all of my reactants, just one of them. All right, lastly, we have temperature changes. And this one is going to depend on if the reaction is endothermic or exothermic. Temperature will behave differently. If it's an endothermic reaction, then we have heat acts as a reactant. And if it's an exothermic reaction, heat acts as a product. So if I increase my temperature, then I'll be increasing a product, which means my equilibrium will shift towards the reactants. And if I decrease my temperature, then I've reduced the amount of my products. And so I'm going to shift to form more of them. I'll shift right, my reaction right. Whoops, sorry, that just went everywhere. My fingers hit it strangely. So the opposites for the endothermic reaction. If we have heat as a reactant, if we increase our temperature, then we're increasing the amount of a reactant and we'll actually form products. So we'll shift our reaction to the right. And if we decrease our temperature, we've reduced the amount of a reactant. We're going to shift our reaction to fill them in, to make more reactants. We'll shift left. All right, hopefully that is a reasonable summary of all of Chapter 6 to help you prepare for the exam.